theorem on basis let V be a finite dimensional vector space. That is, dimension of V is finite. And suppose dimension of V is equal to n. Then any set, number one, prove that. Then one, any set with n linearly independent vectors in V is a basis for V. And any set with n vectors which spans V is a basis for V. So these are the two combination of two theorems. So what is given? Dimension of V is n. Then what is the first theorem? That if set is linearly independent and contains n vectors, then it is a basis for V. Actually, when the set is basis for V, if the set is linearly independent and set spans V. But this theorem says that if we know the dimension of that vector space, suppose the dimension of V is n, means we know that the number of vectors in a basis is n. That is, basis for V contains n vectors. And if we are given any set with n vectors, and the set is linearly independent, then set is a basis for V. That is, there is no need to show the second condition that V spans V, that set spans V. So if the set is linearly independent, but when the set is linearly independent and if the set contains n vectors, at the dimension of V is n. So if the dimension of V is n, and if the set contains n vectors and the set is linearly independent, then set is a basis for V. So no need to show the second condition, V spans, that set spans V. And the second condition, second theorem is what? Any set with n vectors, that is, if the dimension of V is n, and if we are given the set which contains n vectors, and that set spans V, then it is a basis for V. That is, no need to show that set is linearly independent. That is, these two theorems says that in order to show the set is basis, we have to show any one condition out of the two conditions. That is, either show the set is linearly independent or show the set spans V. But when we use this theorem, if we know the dimension of V, and if the set given to check whether the set is basis for V contains some exactly n vectors, that is number of dimensions, okay, number of vectors in the basis for V. So if we are given the set contains n vectors from vector space V, and if the dimension of vector space V is n, then in order to show the set is linearly set is a basis for V, we have to show any one condition. That is, suppose this is the example now. This example, what is this? Show that this V is a basis for vector space R raised to 3. And we know that R raised to 3, dimension of R raised to 3 is 3. Because any basis of R raised to 3 contains 3 vectors. And so dimension of R3 is 3. And we have to show this V is a basis for R3. And this set contains exactly 3 vectors. And so this set is a basis for R3 if V satisfies any one condition. No need to show that B spans V and B is linearly independent. Just show any one condition, that is, B is linearly independent or B spans V. And we know that out of these two conditions, B is linearly independent. This condition is AG. So in order to show the set is basis for a vector space V, we use the theorem. That is, no need to show the two conditions. But if the dimension of V, that vector space, and the number of elements in that set are equal, that is, dimension of R3 is 3, B contains 3 vectors, and so in order to show B is a basis, no need to show the two conditions. Just just show that B is linearly independent or B spans V. Then it becomes a basis for R3. Okay. So now the question arises that if the set contains that, suppose the dimension of R3 is 3, and suppose the set B contains, suppose 4 vectors, that is not exactly 3 vectors, or 2 vectors, that is more than 3 vectors or less than 3 vectors, then what happens? Then that set is not basis for R3. Then we can write in one sentence, no need to show the two conditions. or one condition, single condition in that case, because any two bases, there is theorem that any two bases, this is the theorem. If V is a vector space at its dimension, finite dimensional, then any two bases of V have the same number of vectors. So once this is basis for V, it contains three vectors, and then for any basis of R3 contains exactly three vectors, not less than three vectors, not more than three vectors, because any two bases, that is all bases of R3 contains three vectors. They may be, it may be different from these three vectors, but the number of vectors in any basis of R3 is 3, because dimension of R3 is 3. Once this is basis, means this contains three vectors, and so any basis of R3 contains exactly three vectors. That is, no set contains less than or more than three vectors from R3 is basis of R3. So if the set contains two vectors from R3, or four vectors from R3, five vectors from R3, one vector from R3, that is, then it is not basis of R3. So when the set is basis for R3, if the set contains exactly three vectors and the set is linearly independent or set spans V. So in order to, in all, what is the use of this theorem? In order to show the set is linear, set is basis for vector space V, no need to show the two condition that V spans V, that set spans that vector space V, and the set is linearly independent. Just show any one condition. But when, if the number of vectors in that set is equal to dimension of that vector space, and if these two are not same, that is the number of vectors in the set is not equal to dimension of that vector space V, in that case we directly write that the set is not basis for that vector space V, because any two bases have the same number of vectors. That is, once the dimension of V is n, we know the dimension of V is n, then the set contains more than n vectors or less than n vectors from V is not basis for V. And if the set contains exactly n vectors, then when that set is basis for V, if that set is either linearly independent or that set spans V. So we have to prove the theorem. So the proof of first. So suppose dimension of V is n, and let B is equal to V1, V2, Vn be linearly independent set of n vectors in V. So any set with n vectors, n linearly independent vectors in V. So we take the set of n vectors that contains n vectors and which is linearly independent from a vector space V. So this B is V1, V2, Vn, be linearly independent set of vectors in V, in capital V. Okay. So this set contains n vectors. So now we have to show this is a basis for V. We have to show is a basis for V. And in order to show the basis for vector space V, we have to show B is a linearly independent and B spans V. B spans V. But here we have that B is linearly independent set. Now we have to show only B spans V. So in order to show B basis, we have to show B spans V, because already this set is linearly independent. So after completion of this theorem, in order to show the set is vector space, set is basis for vector space, we prove any one condition. But in this theorem, we have to show this is linearly independent. Now, when this set B is basis, if it is linearly independent and this set spans V, already this is linearly independent. Now B spans V. So we have to show B spans V. When B spans V, if every vector of capital V is expressible as a linear combination of vectors in V. So we know that when B spans V, if every vector of V is expressed as a linear combination of vectors in V. So let V bar is equal to belongs to capital V, be any vector such that V bar does not belong to V. So we take another vector other than V vector. Write this such that V bar belongs to B, or don't write V bar V bar does not belong to B. And let V1 is equal to V1, V2, Vn, then V1, V2, Vn, comma V. So if what happens if V bar belongs to B? then if V bar easily expressed as a linear combination of V1, V2, Vn. So if V bar belongs to B, then V bar is either V1 or V2 or Vn. Suppose V bar is V1, then V1 expressed as a linear combination of V1, V2, Vn such that V1 bar is equal to V1 V1 plus 0 V2 plus dash 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 0 Vn. That is V1 expressed as a linear combination of V1, V2, Vn in a very easily manner. So if V bar belongs to B, then it is either V1 or V2 or Vn. Suppose V bar belongs to B and V bar is equal to V2, then how can write this V bar, that is V2, as a linear combination of V1, V2, Vn? That write V2 bar as a 0 into V1 plus 1 into V2 plus dash 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 0 plus 0 into V3 plus dash 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 0 into Vn. So if V bar belongs to B, then we have to show V bar as a linear combination of V1, V2, Vn, and we can easily show it is a linear combination of V1, V2, Vn. So we suppose V bar belongs to B, but V bar does not belongs to B. Then let B1 with form the new set, that is V1, V2, Vn, and add this V in this B. So we have this set. Then B contains more than n vectors, and the dimension of V is n, and so this set is linearly dependent. So this set B1 is linearly dependent because B contains n plus 1 vectors from V, and so the set is linearly dependent because of theorem. If dimension of V is n, then any set contains more than n vectors from vector space V is linearly dependent. So this set contains n plus 1 vectors and the dimension of V is n, therefore this B1 is linearly dependent. And therefore there is this scalars K1, K2, Kn plus 1, all right, K. We take K1, K2, Kn, K, or Kn plus 1. That is, this set contains n plus 1 vectors, n plus 1 vectors. So take K1, K2, Kn, Kn plus n plus 1 vectors. Be scalars, not all 0. Why not all 0? Because this set B1 is linearly dependent. Not all 0, but their linear combination is 0. That is K1 V1 plus K2 V2 plus Kn Vn plus Kn plus 1 V is equal to 0. If we take this Kn plus 1, then write here Kn plus 1. Or we take K as a scalar of n plus 1 number K. So K V bar is equal to 0. Either take here Kn plus 1, or if I have to take K, write here K, Kn, then K. So K1, K2, Kn, K, be scalars, not all 0, such that this K1 V1 plus K2 V2 plus Kn Vn plus Kv bar is equal to 0. Because S is this B1 is linearly dependent, so all these scalars are not equal to 0. So if K is 0, then what happens? If K is 0, then this is equal to 0, and then we have K1 V1 plus K2 V2 plus Kn Vn is equal to 0, and this set V1 V2 Vn is linearly independent. It is our assumption that this V1 V2 Vn is linearly independent, and therefore this equation K1 V1 plus K2 V2 plus Kn Vn is equal to 0 implies K1 K2 Kn all are equal to 0, as V1 V2 Vn are linearly independent. And this is not true, that K1, if you take K is 0, then we have K1 K2 Kn is 0, and then what we have in all K1 K2 Kn K all are equal to 0. And this is not true, that all are equal to 0. Not all these K1 K2 Kn K are not all 0, and therefore K is not equal to 0. So K must be not equal to 0, and therefore we have from start, that is shift this minus this K V bar to RHS. So we have minus K V bar, and then interchange the sides, and then multiply by minus 1 by K, or divide by minus K throughout. So we have V bar is equal to minus K1 by K V1 minus K2 by K V2 minus Kn by K V1. And all these minus Ki divided by K are scalars from I runs from 1 to n. That is, all these minus K1 by K, minus K2 by K, minus Kn by K, all these are scalars. And therefore what we have, V bar, this RHS is what? Is a linear combination of V1, V2, Vn. That is, V bar expressed as a linear combination of V1, V2, Vn. And therefore we said that every vector of V, this V bar is any vector. And so we say every vector of V is expressed as a linear combination of vectors in B, that is V1, V2, Vn. And therefore B spans B. And therefore B is a basis for B, because already B is a linearly independent set, and we have shown that B spans V, and therefore we say B is a basis for V. The second number theorem, we have to take the dimension of V is n, and we have to take the set contains n vectors which spans V. So let the dimension of V is n, and let V is equal to V1, V2, n be set of vectors in V that contains n vectors, and such that B spans V. And now to prove B is a basis for V, that is why to show B is linearly independent, because already B spans V. So we have, in order to show B is a basis for V, we have to show B is linearly independent. And the proof is by contradiction method. We assume that B is not linearly dependent, linearly independent. We assume that B is not linearly independent, and that is, we assume that B is linearly dependent. Then by above theorem, at least one vector in B is expressed as a linear combination of the rest of the vectors in S. So as suppose if the B is linearly dependent, then one of the vector in this B is expressed as a linear combination of the rest of the vectors in S. This is the property of linearly dependent set. So at least one vector in B is expressed as a linear combination of the rest of the vectors in B. Delete that vector from that set B, or element from B. Delete that vector or element from B, that which one is linear combination of the rest of the vectors. Then let B1 be a new set with n minus 1 vectors. So after deleting that vectors from B, we have the new set, suppose B1, and that contains n minus 1 vector, and still B1 span V. Still B1 span V, because we're eliminating the vector which is linear combination of the remaining vectors, and so still B1 span V. But this is contradiction to the fact that the set with less than vectors than n spans V, because dimension of V is n, and therefore no set less than n vectors spans V. And so this contradiction shows that B is linearly independent. So this is wrong, that B is linearly dependent. So if the B is linearly dependent, we have contradiction. That is, we have the set which is contains less than n vectors and which spans V. As the dimension of V is n, so no set less than n vector spans V. Therefore, B is linear. This is wrong. This B is linearly dependent is wrong, and therefore B is linearly independent, and therefore B is the basis for vector space V. Hence theorem. That is, this theorem indicates that, give the suggestion that if the dimension of V is n, and if the set contains n vectors, then in order to show that set is basis for vector space V, you have to show either any one condition out of the two conditions. That is, either show that set is spans V, or show the set is linearly independent. So example on this theorem, that show that the set is 1, 1, 1, 0, 1, 1, 0, 1 minus 1 is basis of R3. So since the dimension of R3 is 3, and this set B contains 3 vectors from R3. This set contains 3 vectors from R3, and so B is a basis for R3 if B is linearly independent. So just show B is a linearly independent, and already the proof of this set as a linearly independent is given in the previous lecture. So denote these elements as V1 bar, V2 bar, V3 bar, and then write the sentence that K1, K2, K3 be scalar such that K1 V1 bar plus K2 V2 bar plus K3 V3 bar is equal to 0 bar. Write the values of V1 bar, V2 bar, V3 bar. Then apply the definition of scalar multiplication, vector addition, and then we have the values of all K1, K2, K3 are equal to 0. And therefore, we say the set is linearly independent. And then write this statement that since dimension of R3 is 3, after that, so first show this set is linearly independent, and then after that write the sentence that since dimension of R3 is 3, B contains 3 vectors from R3 and B is linearly independent, so B is a basis for R3. So in order to show this set is a basis of R3, we have to show just this set spans V, or this set is linearly independent. So out of these two conditions, linearly, in order to show the set is linearly independent is aged, and the set spans that vector space. So we show that the set is linearly independent. So this is the set of vectors from R3 and contains 3 vectors, and therefore in order to show this set is basis, we show just this set is linearly independent. But if the set contains more than 3 vectors or less than 3 vectors, then no need to show any one condition or two conditions. Just say that this set contains more than 3 vectors or less than 3 vectors, and the dimension of R3 is 3, and therefore it is not basis. So the set contains more than 3 vectors from R3 or less than 3 vectors from R3 is not basis. So determine this set. This is the 2103, 3 minus 1 5 2. This is basis for R3. Determine whether the set is. So the given set is not basis for R raised to 4, because dimension of R raised to 4 is 4, and any basis of R raised to 4 contains exactly 4 vectors from R4, and this set contains 3 vectors from R4. This is first, this is second, and this is third, and so it is not basis for R raised to 4. So determine whether the set contains 1 1 1, 1 0 1 1, 0 0 minus 1, and 0 1 0 is basis for R3. So question is this. So again, the given set is not basis for R3, because dimension of R3 is 3, and so any basis of R3 contains exactly 3 vectors, not less than 3 vectors, not more than 3 vectors. So this sentence is, it does not indicate that every set contains 3 vectors from R3 is linearly is basis for R3. Not every set contains 3 vectors from R3 is basis. So when the set contains 3 vectors from R3 is basis of R3, if that set is either linearly independent or spans V. If the set contains 3 vectors from R3 and the set is linearly dependent, then that set is not basis of R3. Okay, so we have to show this example, show that this set is a basis of R3. So we denote the set elements by V1, V2, V3, and then we have to show this B is a basis of R3. That is show that either B is linearly independent or B spans R3. Just so B is a linearly independent. So in order to solve the example of basis, we have to show the set is linearly independent. So that this is the repetition of the linearly independent dependent type. That is, we have to show this B set B is a linearly independent. So let K1, K2, K3 be scalar such that K1 V1 plus K2 V2 plus K3 V3 is equal to 0. Then K1 write V1 bar, V2 bar, V3 bar, 0 bar. This 0 bar is 0 0 0. Then apply the definition of scalar multiplication and vector addition. We have this. That is multiply by K1, multiply by K2, multiply by K3, and then add the corresponding vectors components. We have this. And then we have the system that K1 plus K2 plus 2K3 is equal to 0. 2K1 minus 3K2 minus K3 is equal to 0. Minus 3K1 plus 2K2 plus 5K3 is equal to 0. Write that system. And then we have to solve the system augmented matrix. So the coefficient of K1, K2, K3, 1, 1, 2, 0, and all this. And we have to reduce this matrix to echelon form. So this is 1. Now we have to reduce this 2 element to 0. So applications transformation are R2 minus 2 R1 and R3 plus 3 R1. So we have the first row as it is, second row, third row. Then minus 1 by 5 R2, because we have to reduce this minus 1 by minus 5 as the element to 1. So we have 1 at that place. We have minus 3 by 5 at this place. First row and third row as it is. Then we have to reduce this 5 to 0. So R3 minus 5 R2. So we have 0. We have here 14, 0. Okay. And we have to reduce this 14 to 1 or remain as it is. So apply one more application, that 1 by 14 R3. Then we have 1 at this place. And that is the echelon form. So rewrite the equation. We have, this is the first equation, this is second equation. Last equation is K3 is equal to 0. So from K3 is equal to 0, substitute K3 is equal to 0 in above equation. We have K2 is 0. And so substitute K2 as 0, K3 as 0 in equation 1. We have K1 is equal to 0. That is, by back substitution, we have the values of K1, K2, K3. All are equal to 0. And therefore, the given set is B is linearly independent. And then write the sentence that as dimension of R3 is 3 and B contains 3 vectors from R3 and B is linearly independent. So by above theorem, the set B is a basis for B, vector space B. So in order to show the set is basis, we have to show either one condition out of the two conditions, any one condition. Okay. So in order to simply we say that in order to show the set is basis, just show the set is linearly independent. But when, if the dimension of V and the number of elements in that sets are same, if the dimension of V, vector space V, and the number of elements in that sets are different, in that case we have to, and in that case we say that the set is not basis for that vector space. That then there is no need to show the two conditions. Even we have to there is no need to show one condition. Directly we can say that, for example, this set contains 4 vectors from R3 and the dimension of R3 is 4, R3 is 3, and this set contains 4 vectors, that is more than 3 vectors, and therefore this set is not basis for R3. This set is the subset of R raised to 4 and the dimension of R raised to 4 is 4, and this set contains less vector than 4, that is this set contains 3 vectors, and so it is not vectors, it is not basis of R raised to 4. So if the set contains more than or less than the number of vectors than dimension of that vector space, then it is not a basis. Okay. So, and if the set contains exactly uh, vectors is equal to the set contains the vectors is equal to the dimension of that vector space, then it is not always a basis for R3. That is, this set is a basis of R3 when this set is a basis of R3 if the set dimension of R3 is 3 and the set contains 3 vectors. So this is not always the basis of R3. So if the set contains 3 vectors, then it may or may not be basis of R3. It may or may not be basis of R3. It is basis of R3 if it is linearly independent or that set spans V. So the set contains 3 vectors. Don't wrong interpretation that if the set contains 3 vectors from R3, then it is a basis of R3. So there are some sets which contains 3 vectors from R3, but it is not basis of R3. That is, if the set contains 3 vectors from R3, then it may or may not be basis of R3. For example, we take 3 vectors from R3 such that the set is linearly dependent. That is, the set is not linearly independent. For example, this example, if you take this set as 2 minus 1 3, 4 1 2, and 8 minus 1 8, so write in curly bracket. So these 3 vectors, the set of these 3 vectors is linearly dependent. This set is linearly dependent, and therefore this set is not basis for R3. For example, v1 v2 v3, and then we have the scalars value of k scalars not all 0, and therefore the given set is linearly dependent. That is, the set of these 3 vectors 2 minus 1 3, v1 as 2 minus 1 3 comma v2 as 4 1 2, and v comma v3 as 8 minus 1 8. So write in these 3 vectors in one curly bracket, and suppose denoted by the set by small s, capital S or small capital B, then this set is not basis of R3. So if the set contains 3 vectors from R3, then it may or may not be basis of R3. But if the set contains more than 3 vectors or less than 3 vectors from R3, then it is not basis of R3. But if the set contains 3 vectors from R3, then it may or may not be basis of R3. So if these 3, if you form the set contains these 3 vectors, then it is not basis of R3 because this set is linearly dependent. So if the set contains 3 vectors from R3, similar sentence to another example, similar sentence for the remaining examples. That is, if the set contains 4 vectors from R4, R raised to 4, then it may or may not be basis of R3. So when the set becomes a basis of R4, R raised to 4, that is, the set contains 4 vectors from R raised to 4, is basis of R raised to 4 if the set is linearly independent, okay, or the set spans V. So these are some standard basis for R square, R raised to 2, dimension is 2, and the standard basis is 1 0 0 1. The set, right? This in the set 1 0 0 1, that is E1 E2 or E1 bar E2 bar. from R2. These are two tuples, 1 0 0 1, and there are two vectors in basis, standard basis. This is the standard basis of R is to 2. Standard basis of R is to 3. Vector space R is to 3. Its dimension is 3, and 1 0 0 0 1 0 0 0 1. This is the standard basis of R is to 3. This is not standard. It is basis, just basis. 1 2 minus 3, 1 minus 3 2, 2 minus 1 5. This is basis of R3. This is not standard basis. It is general basis of R is to 3. So what is the standard basis of R is to 3? 1 0 0 0 1 0 and 0 0 1. We can also denote these elements as E1 bar, E2 bar, and E3 bar. R is to 4. The dimension is 4, and its standard basis is 1 0 0 0 1 0 and 0 0 0 0 1 0, and last is 0 0 0 1. So this is the standard basis of R is to 4. We denote also these elements as E1 bar, E2 bar, E3 bar, E4 bar. The dimension of M2 by 2 R is 4. And what is the standard basis? 1 0 0 0 1 0 0 0. Right here, it is not 2, it is 0. 1 0 0 0 0 1 0 0, then 0 0 1 0, and the fourth element is 0 0 1. So this is the basis, standard basis of M2 by 2R. So any basis of M2 by 2R contains four vectors. So these are the four standard. This is the standard basis of M2 by 2R. So instead of this set of M2 by 2R have another basis. So for example, show that the set 1 0 minus 1 2, 0 minus 1 minus 1 0, 0 minus 8 minus 12 minus 4, 3 6 3 minus 6. This is basis for M2 by 2R. So this is standard basis. Instead of this, we can also have another basis for R, M2 by 2R. But the dimension of M2 by 2I is 4. Therefore, any basis of M2 by 2R contains exactly 4 vectors from M2 by 2R. So if the set contains more than 4 vectors or less than 4 vectors from M2 by 2R, then it is not basis of M2 by 2R. But if the set contains exactly 4 vectors from M2 by 2R, then it is not always basis for M2 by 2R. It may be basis for M2 by 2R. That is, if the set is linearly independent, then it becomes a basis. So in order to show this answer of this example, we have to show this set is linearly independent. Then this becomes a basis. So take K1, K2. This is the repetition of the previous examples. The examples of linearly independent vectors. So let K1, there are 4 vectors, so take 4 scalars. Let K1, K2, K3, K4 be scalars like that. Suppose these vectors are V1, V2, V3, V4. So K1, V1 plus K2, V2 plus K3, V3 plus K4, V4 is equal to 0. Substitute V1, V2, V3, V4 as the, and this is 0. 0 means 0 bar, 0 vector of M2 by 2R. And this is 2 by 2 order matrix, 0 matrix. All entries are 0. So this is the 0 of the M2 by 2R. What is M2 by 2R? It is a vector space. It is a vector space. M2 by 2R is a vector space of all 2 by 2 matrices. Then apply the definition of scalar multiplication and addition in M2 by 2R. That is, multiply by K1 to each element, K2 to each element, K3, K4. And then add the corresponding vector elements. So we have this K1 plus 3K4. Then this entry. Then minus K2 minus 8K3 plus 6K4. Then this entry is minus K1 minus K2 minus 12K3 plus 3K4. And the entry, this entry is what? 2K1 plus 4 minus 4K3 minus 6K4 is equal to 0. So after first write the multiplication definition, multiplication, and then addition. So we have this, and then we have the 4 equation, that is K1 plus 3K4 is equal to 0. Then this is equal to 0, this is equal to 0, and this is equal to 0. So write that system. Now we have to solve this system. So write the augmented matrix and convert the matrix to echelon form, and then rewrite the equation. We have the values of K1, K2, K3, K4 all are equal to 0, and therefore the given set is linearly independent. And then write the sentence that dimension of M2 by 2R is 4, and the set contains, this set contains 4 vectors, and the set is linearly independent, so the set is a basis for R, M2 by 2 R. Okay, so this example is for, these two examples are for homework. So show that x, 3x square and 5 plus x, 5 plus x. Okay, so is a basis for P2x. What is P2x? Set of all vector space of all polynomials less than or equal to 2. Set of polynomials, vector space of polynomials of degree less than or equal to 2. So then another example, determine whether 2x, x square minus 3x, 2x square is a basis for P2x. So it may or may not be basis for P2x. So what is the dimension of P2x? What is P2x? P2x uh, uh, is the vector space of all polynomials of degree less than or equal to 2. So this is the basis. So this set contains 3 vectors, this x, 3x square and 5 plus x. So the dimension of P2 x or P2 is 3. So what is the standard basis? Here we write another member here, P2 or P2x, capital P suffix to x, and the dimension is 3. And what is the standard basis? 1 x, x square, 1 comma x comma x square is the standard basis of P2x. So we in this fashion we could write Pn x or Pn, the set of all polynomials of degree less than or equal to n. The vector space of Pn is what? Pnx is what? The vector space of all polynomials of degree less than or equal to n, and its dimension is n plus 1. The dimension of P2 is 3. Dimension of P3 is 4. In that way, the dimension of Pn is what? N plus 1. And what is its standard basis? Write in bracket 1 comma x square dash dash x raised to n. So these are the n plus 1 elements. So we know that the set 1 x square dash dash x raised to n spans Pn x. So it is a standard basis for Pnx, and so the dimension of Pnx is n plus 1. So if we observe this example, 5, 6x plus x square, 3 minus x square. So what is the answer? This set is linearly dependent, so it is not basis. This set P1, P2, P3, this set is not linear, is not basis because it is linearly dependent. So when the set from P to X is linear, is a basis if it is linearly independent. So we observe in a spanning topic that 1x and x square spans P to X. This 1x x square spans P to X, and means 1x 1 comma x square. This set is a basis for P2x, and it is standard basis for P2x. This 1 0 0 0 1 0 1 0 0, these 4 vectors spans M2 by 2R. So when the dimension of M2 by 2R is 4, and this set spans M2 by 2R, means this set is the basis of M2 by 2R. So in order to show the basis, so this set spans R2, therefore it is the basis. This set spans R is to 4, therefore it is the basis. This sets 1 0 0 0 1 0 0 0 1 spans R3, therefore it is a basis for R3. Or these sets are linearly independent. 1x x square is linearly independent in P2x, this set, and therefore the dimension of P2x is 3. Similarly, the dimension of Pnx is what? N plus 1. And what is its standard basis? Write in curly bracket 1 comma x square comma dash 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 x raised to n. So n plus 1 elements, 1x x square dash 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 x raised to n. So this is about the basis, linearly independent dependent set, and set spans that vector space V. So all these 3 topics are interlinked with each other. That is, in order to show B is a basis, we have to show B is linearly independent, or either B spans that vector space V. So we'll see some more examples on this topic in the next lecture. Some more examples on this topic. in the next lecture. The next topic is coordinate and coordinate vectors. So we see some more examples on linearly dependent and independent. I will share some more examples with you through WhatsApp. So also the examples for homework on the topic basis, that is on the topic linearly dependent, independent, and spanning. So we will see the examples on this topic in the next lecture.